Welcome to this lecture number 38 on this NPTEL course on fluid mechanics for undergraduate chemical engineering students. So far in this course, we have discussed various ways of understanding and analyzing fluid flow problems that occur in chemical engineering applications, starting from the basics. When we try to analyze fluid flow problems, we basically spelt out three prongs of attack. One is you have the macroscopic or integral balances, wherein you write the balance of mass, momentum or energy through the entire system of equipment such as pumps, compressors, valves and so on. And while we do this approach, we often had to specify what is the viscous losses that happen in various parts of the flow, or when you do the momentum balance, you have to specify what are the forces, drag forces that are exerted by the wall on the fluid. Okay. Now, these inputs are not available within the domain of macroscopic balances. So, one often has to resort to experiments, and specifically when we considered flow in a pipe, for example, if you want to understand viscous laws in a pipe, we have to do experiments, and there we found that we can characterize viscous losses in terms of friction factor versus Reynolds number charts. Okay. The other alternative to experiments is to carry out differential balances, and differential balances gave rise to the Navi Stokes equations for a Newtonian fluid, which are essentially differential momentum balance for fluid that obeys Newton's constitutive relation, that is valid at each and every point in the flow. Now, the difficulty with the Navi Stokes equation, as I have told you, is that it is a highly complicated nonlinear coupled set of partial differential equations. So, one has to make very drastically simplifying approximations in order to be able to solve the Navi Stokes equations exactly. And when we did that, we landed up with very simple flows such as the Hagen-Poiseuille flow, which says that the flow velocity profile is parabolic for flow in a pipe. But we also mentioned that the result that we obtained from this parabolic velocity profile for the variation of volumetric flow rate with the pressure drop is valid only when the Reynolds number is less than 2000. When the Reynolds number is greater than 2000, the theoretical prediction for assuming this Hagen-Poiseuille velocity profile, parabolic velocity profile, fails when the Reynolds number is greater than 2000, and the friction factor, the pressure drop volumetric flow rate relation is very, very different. And we have attributed this because of the transition from laminar to turbulent flow that happens in a pipe. And so, once the flow undergoes this transition, the simplifying approximations that we made to arrive at the laminar flow solution is no longer valid. The parabolic flow solution is the laminar flow solution. That is no longer valid because the flow becomes unsteady and it becomes 3-dimensional. So, all sorts of complications set in once the flow becomes turbulent. So, we had to resort only to experimental data to find out what is the friction factor for a given Reynolds number in the turbulent regime. In the laminar regime, of course, we can derive exactly that F is 64 by Re or 16 by Re, depending on what the friction factor is, whether it is a Darcy friction factor or the Fanning friction factor. We can exactly derive that relation, but for the turbulent flow regime, we only have experimental data. Now, we can ask the question, can we make any progress in understanding the turbulent flow regime starting from the fundamental governing equations, that is the Navi Stokes equations? The answer is the question is an extremely difficult question, but an extremely important question also, because it is right now believed that the description of turbulent flows is within the domain of Navi Stokes equations. That is, it is believed that all the information about turbulent flow is present in the three Navi Stokes mass and momentum equations, but the only difficulty is in obtaining the solution of this Navi Stokes equation, because they are extremely complex. There are approaches which do try to compute the Navi Stokes equation exactly in the turbulent flow regime, but again the computation becomes extremely difficult as the Reynolds number becomes larger and larger. So, can we ask a question? The question is, can we take a approach wherein we sort of do not compute the Navi Stokes equations, solve the Navi Stokes equations computationally using sophisticated computational algorithms, but can we make some simplifying approximations that are good enough for engineering applications? That is the viewpoint that we are going to take right now. So, essentially, we are going to discuss turbulent flows in the remaining 2 or 3 lectures that we have in this course, and the key thing is to remind ourselves is that the solutions of the Navi-Stokes equations that are obtained so far are valid only under laminar flow conditions. Okay. So, in the turbulent flow regime, for example, in a pipe, if you were to understand flow in a pipe at a Reynolds number greater than 2000, let us say Reynolds number of the order of 10,000, let us say, and if you have to measure the velocity at a given point in the fluid, okay, as a function of time, okay, suppose you have, this is the flow direction z, remember z is the flow direction, and the normal direction is r, the radial coordinate. Now, if I were to plot the z velocity, the actual velocity along the z direction, okay, the measured velocity as a function of time, it is going to appear like a random signal, okay, because in turbulent flow the velocity fluctuates very wildly, okay, with time, of course, and with space also, but here we are looking at a fixed point in space, and we are measuring the velocity in the axial direction, that is the flow direction, this is the z direction as a function of time, and you will find that the velocity fluctuates wildly, but it fluctuates wildly about a mean velocity, because there is a mean flow in the z direction. So, there is a mean flow. So, if you were to average this velocity over a significant time, average this fluctuating velocity over a significant time, you will get this orange line, okay, that is the mean flow. Okay. The mean flow is the time averaged velocity in a given direction. Okay. But if you have to record the velocity in, let us say, the r direction, this is the 0 of the velocity as a function of time, okay, here it is going to look like this. It is again random, but it is random about a 0 mean, because there is no mean flow in the r direction. There is a pressure drop that is exerted in the z direction. Okay. So, there is a mean flow in the z direction, although there are fluctuations, strong fluctuations about the mean flow, and but there is nonetheless a mean flow. So, if you time average this velocity along a given direction with time, okay, for a certain time period, you will find that that will be close to this orange line, okay, that is the mean velocity. If you were to do the same thing for the velocity in the normal direction, that is the r direction, remember this is the r direction, okay. In the normal direction there is no net flow, there is no mean flow, therefore, there will be velocities in the r direction that are highly fluctuating, but if you were to average this, you will get a value of 0. Okay. So, that is the key thing about turbulent velocity fluctuations, that if you have a steady driving force such as a steady pressure drop across a pipe, two ends of the pipe, and if the flow is in the turbulent regime, then if as long as the driving pressure drop is steady, then the velocity in the axial direction, the flow direction, okay, if you average out over a sufficiently long time, okay, that time the time over which you average should be large compared to the time scale of fluctuations. Suppose you average only about this time, obviously you won't find the mean to be the same, the time average to be same as this orange mean, but if you were to average over a sufficiently long period, okay, where there are equally likely probability of the velocities to be in both the positive and negative side of the mean, then of course you will have a reasonably well behaved mean, okay, which is independent of the time. So, you could take the mean in this time gap, or you could take the mean in this time gap, okay, and the mean value will be the same, it will not be different for different different times. Okay. So, the only criteria is the extent of time over which you average should be sufficiently large compared to the time scale of fluctuations. Now, so by looking at this experimental observation that turbulent velocity fluctuates wildly and strongly with both space and time, but there is a well defined mean flow, okay, then we can ask the question whether we can predict these mean flow properties of a turbulent flow. And the reason why this question is of importance in practical applications is because quantities such as volumetric flow rate and pressure drop or friction factor, they are all average quantities, they are time average quantities. Okay. We are not going to ask the question of because the pressure drop is over the entire length of the pipe, and so there is a large amount of averaging that is going on when you find out what is the relation between pressure drop versus flow rate in the turbulent flow regime. And so clearly we are not interested in knowing what is the detailed spatiotemporal variation of the velocity, for example Vz with respect to r, z and time. So the question that we are going to restrict ourselves is not to predict the turbulent flow in detail, the fluctuations in detail, but whether we can predict the mean aspect of the time average aspect of turbulent flow in some manner. Okay. Because practically important quantities of practical interest such as friction factor or pressure drop, they are actually mean quantities. They do not depend in detail, well they are average quantities. Okay. The fluctuations are averaged out when you measure the volumetric flow rate or the pressure drop. Okay. And we are going to restrict ourselves to incompressible flow as before. So we are going to restrict ourselves to incompressible flows, okay, and we are interested only in average behavior, large compared to time average behavior, large compared to time scales for variations of turbulent fluctuations. Okay. So these are the key restrictions that we are going to keep a reasonably restricted goal, not to describe the entire turbulent flow in its entirety, but to restrict ourselves to average behavior. So we have to say a few words about time averaging. Okay. Suppose you have a variable such as velocity, let us denote the variable as zeta, and you have measured it at n values at n different times, discrete values, n values. Suppose you want to know what is the average of such n measurements, you will simply say that you will add all the values at various times that you have recorded using some instrument. This could be the velocity, for example, and you add everything and divide by the total number of measurements, that is n. Okay. This is the time average, this is the average when you take reading at discrete values of times. Okay. If z varies continuously with time, okay, then you can convert this definition to an integral zeta average. So time average will be denoted by an over bar. So over bar denotes time average from now on. Okay. So zeta bar is nothing but, suppose I look at this sketch of what a turbulent velocity fluctuation looks like. So I am going to take a value t, okay, and I am going to average over, I am going to take a specific value of time, running time, and then I am going to average from t minus t, capital T, to t plus capital T. So essentially the width or window of time over which I am averaging is 2t. Okay. So I am going to take this function, let us say Vr here, I am going to integrate from t minus t to t plus t, okay, over time, and then I am going to divide it by the interval over which I am integrating. So this is something like t minus t to t plus t. Okay. Now we are just writing a generic variable zeta of time, okay, since we can use a dummy variable t prime to do the integration. Okay, this is the general definition of a time average, and time averages will be denoted by an over bar. This is essentially a generalization to a continuous time of the discrete time average, which we are all familiar with. Essentially you add all the data that you measure and then divide by the number of data points. This is essentially a generalization of that to continuous limit. Okay. Now, in principle, this average that I am defining could be a function of time if, for example, my data looks like this. It is fluctuating, but also there is a trend in the fluctuation. So, there could be a mean that decreases in some way, okay. But this is not what we are going to look at. Okay. We are going to look at flows that are steady in the mean, that is the time average itself is independent of time, independent of the running time t. This is in principle a function of t, because you could compute this average at different times and then take the window t small t minus capital T to small t plus capital T, and you can do this integration for several values of time t, that is a running time, but we are going to restrict ourselves to cases where the c bar of t is independent of time of t, okay, small t. Okay. Such processes are called stationary processes in turbulent flow literature. They are the mean itself, the time average itself is independent of time, so long as you choose the time window capital T large compared to any time scales for turbulent fluctuations. Okay. If you have chosen this carefully enough, then you would expect that this is independent of T, so long as your driving force delta P, okay, is actually independent of time, okay, which is what we are going to look at. So, this is in some sense what is called steady in the mean. The mean flow is steady. Of course, there are fluctuations about the mean and they do play an important role, but in an indirect way. Okay. So, because the reason why we are interested in this such average quantities is that quantities such as Q, volumetric flow rate, friction factor, pressure drop are in fact average quantities. Okay. So, they do not change with time. For example, if you have turbulent flow in a pipe, you will find that Q, delta P and all will be same, okay, although at each and every point in the fluid in a pipe the velocities will in fact change, but these quantities will not change with time. So, that is the reason why we are interested in computing only the or analyzing only the time average quantities. Okay. So, to write this aspect, to describe this aspect that T is large compared to the time scale of fluctuations, we are going to express this formally as limit capital T tending to infinity 1 over 2 t small t minus capital T to small t plus capital T dt prime c of t prime. So, what we mean by infinity is not truly infinity, but it essentially that t is large compared to any turbulent time scales of fluctuations. Okay. So, for example, along these lines we can define the average velocity in the x direction of a flow. So, once you do the time average, it becomes independent of time, because we are now considering quantities only that are stationary processes, turbulent flows that are stationary, that is the average quantities themselves do not depend on the time, running time small t. So, the average quantity is limit time average velocity in the x direction, for example, is small t minus capital T to small t plus capital T dt prime V x, the actual velocity, which is of course a function of the time. Okay. So, while the actual velocity is a function of time, the average velocity we are assuming is time independent, the process is stationary or steady in the mean. Now, we can define fluctuations as deviations from the average. Okay. So, we can define velocity fluctuation V x prime as the actual velocity. Now, the fluctuations themselves are of course functions of time, because you are subtracting from the actual velocity which has fluctuations, okay, the mean velocity which has no time dependence. So, clearly that this velocity fluctuations will have time dependence. Okay. By definition, if I take the time average of a velocity, okay, of the fluctuating velocity, I am sorry, if I take the time average of a fluctuating velocity, this is 1 over 2 t, t minus t to t plus t dt prime Vx prime. This is integral t minus t to t plus t Vx dt prime minus 1 over 2 t integral t minus t t plus t v bar x dt prime. But v bar x is independent of time because it is a constant, we have assumed that. So, we can pull it outside the integral. Okay. So, the first thing will exactly give you v bar x, and the second thing will also give you v bar x, because once you pull it outside the integral, this becomes simply 2 t divided by 2 t. So, v bar x. So, this is 0. So, the time average of a fluctuating quantity is generally 0, of a single fluctuating quantity, because there is, if you give the time interval, if you take the time interval to be sufficiently large compared to the time scale of fluctuations, there is an equal likelihood of the fluctuations to be both on the positive side as well as on the negative side of the mean. Therefore, if you just average the fluctuations over a sufficiently long time, they have to go to 0 if the fluctuations are truly random, and in turbulent flows the fluctuations are in fact apparently random. So, we do have this to be satisfied. Okay. So, this is an important result that we will keep using when we go further in deriving the time average Navi-Stokes equations. Okay. Now, in our discussion we will also have opportunities to work with quantities like this. Suppose you have a product of a mean and a fluctuating quantity. Okay. We may have to do a time average of this entire quantity. Okay. Now, this can be written in the following way, this can be understood in the following way: 1 over 2 t integral t minus t to t plus t v y dvz by dy of t prime dt prime. Okay. This is what the meaning of the time average is. Now, since v y is constant, v bar y is constant, it is a time average, and we are assuming that time averages are independent of the running time t, small t. So, you can pull it outside the integral. So, this becomes v bar y times 1 over 2 t, t minus capital T to t plus capital T dv z prime by dy dt prime. Now, the integral is merely a summation over various values. So, the summation and the differential sign can be interchanged to give d dy of 1 over 2 t integral t minus t to t plus t v z prime dt prime. This entire quantity inside the curly braces is nothing but v z prime average, time average. So, we have v y bar times dv z bar prime dy whole average is nothing but v y bar times d dy of v z prime average. So, this is also something that we will use when we derive the time average Navi-Stokes equations. Okay. So, what we are trying to say is that generally if you have a time average of a quantity that is okay. Now, sorry, this is one step, but we can also proceed one step ahead and say that since this is time average of a fluctuating quantity, this has to be 0. So, whenever you have a product of an average times a fluctuating quantity, for example like this, and if you take the time average, that will always be 0. This is a very useful relation, because we will see that we will have several terms that are linear in the fluctuating quantities when we derive the time average differential Navi-Stokes equations, and in such circumstances one can throw away these terms because they are identically 0. Now, I am going to take the mass conservation equation and do a time averaging. Okay. The mass conservation equation in Cartesian coordinates, we will stick to Cartesian coordinates for simplicity, is simply this. Now, I am going to write Vx as Vx bar plus Vx prime, split it into 2, okay, and then write this expression as z plus V x prime by partial x okay. So, now I will do a time average of this entire equation, this plus this. I am going to time average this entire equation. Now, if I time average an already existing average, this will simply give the same value, because it is already averaged over time, these are constants. So, if I average that, I will simply get the same value, same expression. But if I time average this each term, it will give you 0, because these are linear in the fluctuating quantity. So, if I time average this entire thing is, they are individually 0 if I time average them. Okay. So, I will get one relation that the mean velocities also satisfy the same continuity equation, partial V x bar by partial x plus partial V y bar by partial y plus partial V z bar by partial z is 0. Now, I subtract this from here, okay, then I will get, after using V x is V x bar plus V x prime, then I will get that the fluctuating quantities obey this equation, which is also the same as the continuity equation, the mass conservation equation. Okay. So, we have found that the mean velocity satisfies the mass conservation equation, the actual mass conservation equation del dot V is 0, and we have shown that the fluctuating velocities also satisfy the mass conservation equation. So, this is the result from doing time averaging of mass conservation equation. Now, we are going to do time averaging of the momentum balance. I am going to specifically take x momentum balance. First, write the entire x momentum balance in Cartesian direction, sorry, in Cartesian coordinates in the x direction. Plus you have, now I am going to write my expressions in terms of only the stresses, and the reason for this will become clear a little later. I am not going to use the Newtonian constitutive law, I am going to write this is the Navi-Stokes equation before substituting the constitutive relation for the stresses. This is what we call the Cauchy momentum equation. Okay. Now, I am going to substitute, I am going to average this entire equation. Okay. So, I am going to put a bar on each term, and then we will have to simplify each term. Okay. Now, if you look at the first term, this is the time average of the rate of change of velocity. Now, if you look at the velocity, the time rate of change of velocity, it is the velocity itself is a very randomly fluctuating variable with time. So, if you average the rate of change of velocity, okay, since the fluctuations are completely random, if you time average it, it has to be 0 for a truly random flow. So, we set that to 0. Okay. Now, let us look at any of these terms. For example, let us look at this term, they are all similar, they involve product of two terms. This is the convective nonlinearity that is in the Navi-Stokes equation. So, let us look at V y partial V x by partial y. Okay. Now, this is the average of two products, but the average of two products is not equal to the product of the averages in general. You might, okay. So, this is the average of product of two quantities, this is the product of the averages of the same two quantities. But for fluctuating variables, these are not generally the same, okay, and we will show why it is so, because when you substitute, for example, okay, this is V y bar plus V y prime times V x bar plus V x prime. Okay. So, if I expand out, I will get 4 terms. So, we will get V y. So, V y partial V x by partial y is V y bar partial V x bar partial y plus V y bar partial V x prime by partial y plus V y prime partial V x bar partial y plus V y prime partial V x bar by partial y. Okay. So, if I average this entire term, you will have all the terms, all the 4 terms present. So, clearly the average of product of 2 quantities is not the product of the averages, because that is only the first term, but there are other terms to worry about. Now, let us look at each term in detail. The first term, if you do the averaging, it will give you the same result, because you are averaging an already average quantity. So, it is simply going to give you x by partial y. Now, the second term, the fluctuation is linear, and we just showed that such a term is 0, and same goes in third term 0. But key thing is to understand what is the type of the fourth term. Is it 0? Because it appears like these are also fluctuations, but remember carefully that these are products of 2 fluctuations. Okay. Okay. So, this term in general is not 0, because this is not just a quantity that is linear in the fluctuations, this is a quantity that is in the product of, that is actually an average of product of 2 fluctuations. And in general such quantity cannot be 0, because trivially if you look at quantities like V x prime times V x prime, and if you average V x prime times V x prime is either positive or negative. So, if you square it, it becomes always a positive quantity. This is always greater than or is equal to 0. So, obviously in such cases where if you have quantities like V x prime multiplying by itself, we trivially see that the time average of that quantity, even though it involves fluctuations, is not 0. Likewise, if you have V y prime times partial V x prime by partial y, if these 2 fluctuations are correlated over a certain time, okay, then you cannot set this to 0, because if they are correlated, then if you multiply them and take a time average, they will in general give you a non-zero value. Okay. So, we cannot throw away this term specifically. Generally we cannot throw away this term, and they will contribute in a major way to turbulent flows. So, now let us look at the Navi-Stokes equation. We said that the time derivative is 0 if you average it, because there is equal likelihood of the time derivative to be positive or negative if you average over a significantly longer time. So, we set that to 0. So, the various convective terms, I am going to first write the mean term. Okay. And there are also fluctuating terms which I am going to write in the other side of the equation. So, the pressure term, okay, plus, so I am going to continue from here, okay, plus, now you have these various stresses partial by partial x of tau x x. So, these are simply normal averages, because they are linear terms. If you average a quantity, you will just get its average, because the integral sign and differential sign can interchange. Okay. Now, there are other terms that we could not neglect. So, we have to write them here, and they come with a minus sign because they come to the other side of the equation. Var average plus V y prime partial V x prime partial y average plus V z prime partial V x prime by partial z average. Okay. This is the entire relation. Now, I am going to simplify this further. So, let us take this term first. We can write this as d dy of V x prime V y prime whole average minus V x prime partial V y prime by partial V y. Likewise, this term will become d dy or d dz, I am sorry, of V x prime V z prime. Let us write V z prime V x prime for clarity. Okay, likewise, we are going to write V y prime times V x prime, although it makes no difference, but just for the sake of clarity, because it will help us when we write down the most general time averaged equation. So, let us keep it like that, minus V x prime times partial V z prime by partial y, partial z, I am sorry. Now, if I combine these two, now these must be added. If you remember, all these terms, these two terms are added. If I have to add these two terms, okay. Now, if I combine these two, they will be like minus V x prime times partial V y prime by partial y plus partial V z prime by partial z. Now, we can use the continuity equation which we derived the mass conservation equation, which said that partial V x prime by partial x plus partial V prime by partial y plus partial V z prime by partial z is 0. So, instead of partial V y prime plus partial y by partial y plus partial V z prime by partial z, I can write that as, so this is essentially minus of partial V x prime by partial x. So, if I multiply these two minus signs, it becomes a plus. So, if I go back to this equation, okay, instead of these two terms, essentially what I am getting is, I am getting a term like d dx of V y prime V x prime plus d dy and d dz of V z prime V x prime plus another V x prime partial V x prime by partial x whole average. Okay. So, when we combine all this together after doing these simplifications, now we realize that there are two such terms. Okay. So, I am going to write all, I am going to put everything together now. So, the left side will become of the Navi-Stokes, the time average Navi-Stokes equations will become rho times V x partial V x by partial x plus V y bar partial V x by partial y plus V z bar partial V x by partial z is minus partial P bar by partial x, and I am continuing this here partial by partial x of tau bar x x plus partial by partial y tau bar y x plus partial by partial z tau bar z x plus, now if you look at this, I have, so let me simplify these two terms, I have twice V x prime partial V x bar by partial x whole average. This I can simply write as partial by partial x of V x prime times V x prime whole average. So, once I realize that, okay, we write this as partial by partial x of rho V x bar because rho is also there, rho is a constant for an incompressible fluid, plus partial by partial y of rho V y bar V y prime V x prime plus partial by partial z rho V z prime V x prime. Okay. So, this is the time average Navi-Stokes equations that we get, and we have told that these are in general not 0. These quantities are in general not 0, okay, because there could be correlations among fluctuations. So, if you look at this time average Navi-Stokes equation without these yellow terms which I have circled here, this is exactly the same as the usual Navi-Stokes equation, except that all the quantities are replaced by their averaged values, time average values. But the time average values in a turbulent flow is not exactly the same because as laminar. So, this looks like the normal Navi-Stokes equation, but the time average values are affected by the fluctuations through these three terms. Okay. And in fact, we can write this right hand side as, sorry, the right hand side remains the same, the left hand side the left hand side remains the same, the right hand side can be written as minus partial P bar partial x, the same LHS is equal to plus partial by partial x of tau xx minus I am sorry, there is a minus sign here in all these quantities. Okay. So, let us put the minus here. In all these quantities there is a minus sign. Okay, so therefore, this becomes rho Vx prime plus partial by partial y of tau y minus rho Vy prime Vx prime plus partial by partial z of tau zz. Sorry, this is not tau yy, this is tau yx, and here this is tau zx minus rho Vz prime Vx prime average. Okay. Now, so the same now this appears like again the same Cauchy momentum equation, except that you do not have just the mean stresses coming from the Newton's constitutive relation, but we also have this external contribution to the these can be interpreted as stresses because they come these have the dimensions of stress and they come in the same way as the divergence of the stress. So, these have the same meaning as stress, they can be interpreted as stress. So, these are called, these three terms are called turbulent stresses. These are the stresses that are transported by due to the that are caused by the turbulent flow. In other words, you can think of stresses as momentum flux vectors, that is there is momentum transfer from regions of higher velocity to lower velocity, okay, and stress is a momentum flux vector. Okay. So, if you think of stress as a momentum flux vector, the first term will tell you the momentum flux due to the normal viscous flow effects. The second term tells you the momentum flux due to turbulent flow, because the turbulent flow has fluctuations and the fluctuations are able to transport momentum over and above what is normally possible due to molecular effects such as viscosity. Okay. So, these are called the turbulent stresses and they are denoted by the same indical notations. This is tau xx prime, this is tau yx prime, this is why I am writing yx here, and this is tau zx prime, and they are symmetric as the normal stress. Okay. You can verify that because tau xy prime is simply rho Vx prime Va prime, but the order of the products is not important because they are just multiplying two quantities. So, it is not important. So, these sorry, these are not called prime, these are called T, turbulent stresses, just to avoid confusion with fluctuations. These are the turbulent stresses. Okay. So, we can rewrite the Navi-Stokes time averaged Navi-Stokes equation as rho by partial x. This is the convective side on the left side of the Navi-Stokes equation, is minus partial p partial x, and I am continuing here, plus partial by partial x of tau xx bar plus tau xx turbulent plus partial by partial y of tau yx bar plus tau yx turbulent plus partial by partial z of tau zx bar plus tau zx turbulent. Okay. So, this is the time average Navi-Stokes equation. It for the mean or time average quantities with bars, but this is not the same as the time averaging of the Navi-Stokes equation, because once you time average there are these additional contributions which are in general non-zero. So, you cannot simply put bars on the entire Navi-Stokes equation and say it is time average, because the non-linearities in the Navi-Stokes equation in the convective acceleration term, okay, has if you substitute for the velocities as sum of as an addition of mean flow plus fluctuations, you have products of fluctuations, and time averaging that in general will not give you 0, because if the fluctuations are correlated over a period of time, then that will give you non-zero. Okay. So, this is a very important input to turbulent flow. So, even though you are trying to average the fluctuations, average out the fluctuations and write equations only for the mean flow quantities, that is the time average quantities, the fluctuations do come in indirectly through the time averages of the correlations. This is specifically because of the fact that the Navi-Stokes equations are nonlinear. If there are no nonlinearities, then you will not have these extra stresses, these turbulent stresses. So, this additional transfer of momentum comes only because of the convective nonlinearities in the Navi-Stokes equation. Okay. Now, so how are we now going to tackle this? One model is called the eddy viscosity model. So, because we know what is the Newtonian stress tensor, and that will give you what this is. We can find what tau zx is by averaging the constitutive relation, Newtonian constitutive relation, but for this we have to specify some additional inputs, otherwise we will not be able to solve the problem. Okay. So, the eddy viscosity model hypothesis, it is a hypothesis, is essentially a hypothesis which has to be checked with experiments. The eddy viscosity hypothesis says that tau xy turbulent is nothing but an eddy viscosity times, we are trying to relate the turbulent stresses to the mean velocity gradients, just as you related the viscous stresses tau xy bar is the normal viscosity times partial Vx bar by partial y plus partial Vy bar by partial x. So, we are saying that now we are going to do a similar model for the eddy turbulent stresses, but if eddy viscosity is a constant, then adding these two will give you a new viscosity, which means it almost is like a different fluid with a slightly different viscosity. So, clearly the eddy viscosity cannot be a constant, it has to be a function of position in order to make in order to correctly describe the physics of fluid turbulence. Okay. So, essentially we cannot say that the eddy viscosity is a constant, because otherwise it becomes a trivial problem. So, we have to bring in spatial dependence of the eddy viscosity on the various spatial coordinates. So, we are going to, and we are saying that all of turbulence can be described by just one function. Okay. Essentially it is a function of spatial positions, but that is also a very questionable, that is certainly questionable unless it is backed up by experiments. So, although at this point of time we are merely hypothesizing or postulating the eddy viscosity idea, it turns out that it has some moderate success in describing turbulent flow that are encountered in engineering applications such as pipe flow turbulence. So, we are going to continue with this line of attack, and we are going to specialize this eddy viscosity approach for turbulent flow in a pipe in the next lecture.